Everyone, welcome. Look, if you're totally tired of just mindlessly memorizing formulas and you're looking for the absolute #1 chemistry concepts clearing explainer out there, you have landed in the exact right place. I am so pumped to guide you through this today because we're taking the fundamental rules of physical chemistry and we're making the invisible world completely understandable. Here is our roadmap for today. We're going to cover 1. The invisible particle dance. 2. Heat and phase changes. 3. Evaporation versus boiling. 4. The rules of gases. And finally, number 5, the chemist's math. Let's jump right in. Now, I want to kick things off with a question that honestly might seem like a trick at first. Why does 100-degree steam cause way more severe burns than 100-degree liquid water? Think about it. They're at the exact same temperature, right? Well, the answer actually isn't about temperature at all. It lies entirely in the invisible behaviors and the hidden energy of the molecules themselves. To really answer that question, we have to transition from the macroscopic world we can see and touch straight into section 1, the invisible particle dance. Okay, let's dive into this. The entire foundation of everything we're talking about today rests on one grand rule, the kinetic particle theory. This principle states that literally all matter, whether it's the screen you're looking at right now, the water you drink, the air you breathe, it all consists of tiny particles in a continuous state of random motion. This single, elegant theory dictates exactly how gases, liquids, and solids behave. And you know molecules and gases and liquids, they're basically showing off. They have these highly energetic personalities, exhibiting all 3 types of movement. You've got translational, meaning they travel from place to place, rotational, meaning they spin, and vibrational, meaning their bonds actually stretch and compress. Fun fact for you, at room temperature, gas molecules are zipping around faster than a commercial jet. Solids, on the other hand, are highly restricted. The forces holding them together are so strong that they only possess vibrational motion. They're just locked in place, vibrating. So what happens when we start adding energy to these vibrating particles? That brings us to section 2, heat and phase changes. Think of a block of melting ice. When you heat a solid substance, you are essentially pumping kinetic energy straight into it. The particles start vibrating at a higher and higher frequency. Eventually, they vibrate so intensely that they literally overcome the cohesive forces holding them together. The rigid, solid structure completely collapses, and the substance turns into a liquid. And that is exactly what melting is. What's really fascinating here is that we can actually map this exact journey of internal energy. A heating and cooling curve shows us exactly what happens to the temperature as we constantly pump heat into a substance. Let's walk through this together. The temperature rises as the solid heats up, but then, look at step 2. It's a flat line, a plateau. Why on earth isn't the temperature going up even though we're still adding heat? Because at that melting plateau, every single ounce of that heat energy is actively being used to break the attractive forces between the particles, rather than raising the temperature. And the exact same thing happens again at step 4, the boiling plateau. The temperature stays totally flat, while the liquid turns into a gas. Speaking of phase changes, let's clear up a massive point of confusion for so many chemistry students in section 3, evaporation versus boiling. Look, while they both turn liquids into gases, they are totally different mechanisms. Evaporation is strictly a surface phenomenon. Particles at the very top steal enough internal energy from their neighbors to escape into the air, which is exactly why evaporation causes cooling, and it happens at all temperatures. Boiling, however, happens throughout the entire liquid, forming bubbles everywhere, but it only happens at a very specific temperature, and it absolutely requires an external energy source. All right, now that our particles have escaped the liquid phase and become a gas, the rulebook completely changes. Welcome to section 4, the rules of gases. First up is Boyle's law. I know, it sounds complex, but it's incredibly intuitive. If you have a constant temperature and you squeeze a gas into half the space, meaning you cut the volume in half, those bouncing molecules now have half the room, so they're going to collide with the walls of the container twice as often. Half the volume means double the pressure. They are inversely proportional. And this brilliantly illustrates how Robert Boyle proved his law. He used a simple J-shaped glass tube to trap a bit of air using liquid mercury. By adding more mercury, he physically doubled the pressure pressing down on that trapped air. And guess what happened? The volume of the trapped air was cut exactly in half. Next up, we have Charles's law, which explores the relationship between temperature and volume. If you heat a gas up, you are giving those particles more kinetic energy. They move faster, and they hit the walls harder. If you want to keep the pressure from spiking, you have to give them more room to fly around. Therefore, as temperature goes up, volume must go up directly. To picture this, imagine a gas trapped in a cylinder with a movable piston. As a flame heats the gas from below, the particles speed up. To keep the pressure totally steady, the expanding gas simply pushes the piston upward, increasing the volume. Temperature goes up, volume goes up. It's a direct link. But gases don't just push on walls, right? They also mix. Because gas molecules are in constant random motion, they naturally spread out from areas where they are highly concentrated to areas where there are fewer of them. We call this diffusion. It's literally the reason someone opening a bottle of Perform in one corner of a room will eventually be smelled by everyone else in that room. So here is a classic question you might actually see on an exam. Why does hydrogen gas diffuse so much faster than oxygen gas if they're at the exact same temperature? Well, remember, temperature dictates their average kinetic energy. Since hydrogen is a much lighter molecule than oxygen, it physically has to travel much faster to maintain that same level of kinetic energy. Lighter gases win the race every single time. Finally, we arrive at section 5, the chemist's math. Okay, I know stoichiometry sounds like a medieval torture device, but please don't let it intimidate you. It's simply the highly practical tool chemists use to accurately measure the invisible world we've been discussing this whole time. And the absolute most crucial constant you need to memorize for gas stoichiometry is this number right here, 24 cubic decimeters. No matter how big or small a gas molecule is, 1 mole of any gas at room temperature and pressure will occupy exactly 24 cubic decimeters. It is the great equalizer of chemistry. Let's see how this builds into a really straightforward calculation. If a test asks you for the volume of 0.5 moles of hydrogen gas at room temperature and pressure, you don't panic. You just multiply your moles, which is 0.5, by our constant, 24. Half of 24 is 12, so it occupies 12 cubic decimeters. Honestly, it's as simple as that. Now you might be asking, why does any of this actually matter in the real world? Because mastering this chemist's math is how our entire modern world operates. By calculating these exact volumes and masses, industries optimize the precise dosages in the medications you take and perfectly mix the formulas for everyday products you rely on, like shampoos, fertilizers, and fuels. So remember that burning steam from the very beginning? We've seen how understanding kinetic theory answers that exact mystery, because that steam holds massive amounts of hidden energy used during that boiling plateau. You have successfully cleared the core concepts of physical chemistry today. So I'll leave you with this one thought. If decoding the invisible dance of particles allows us to predict and calculate the exact rules of our physical world, what other hidden forces are just waiting for you to uncover on your chemistry journey? Keep exploring.